Good morning, everyone. Welcome and thank you for joining us for the AI-powered build, generative design, robotics, and automation in the future of construction. My name is Joe Broon. I'm the Managing Director of Building Digital and today's host of this online micro conference. Today's session explores one of the most important shifts our industry, every industry, has ever faced. How artificial intelligence is moving from theory into real-world application across the entire construction life cycle. From generative design tools that reshape how we conceive buildings to robotics and automated systems that are transforming how we physically construct them, AI is redefining what's possible. Across this session, you'll hear from leading innovators working at the cutting edge of design technology, robotic fabrication, and intelligent systems. They'll share practical insights, real-world applications, and forward-looking perspectives on how these technologies will shape the future of architecture and construction. We're going to move on to our third keynote of today's micro conference. I'd like to introduce Loris. Loris is head of software and AI at Solskin, Zurich Soft Robotics, and where he leads the development of intelligent systems for adaptive building envelopes. His work sits at the intersection of artificial intelligence, robotics, and material systems, developing responsive facade technologies that can sense, learn, and adapt to environmental conditions. Loris brings deep expertise in machine learning and embedded systems, helping to push forward the integration of AI into the physical fabric of buildings. Loris, you are free to take over your screen with your presentation.
Yes. Hello, everyone. I hope you can see and hear me well. Okay, great. Thank you for the introduction. Yes, as mentioned, I work for Zurich Soft Robotics, which is commercializing Solskin, which you can see here on this picture. So it's a robotic system where we put solar panels on a robotic arm, which can move in 2-degree axis. So it can move in every direction. So it can track the sun, for example. And this typically goes in front of a big window, like here in this picture. And today I want to talk about what happens once this is actually on the building already, because when you bring that kind of technology, you want to make sure that it interacts well with the building and that you do everything as smart as possible. And this is where AI comes into play for us. So essentially, when you try to think about how to optimally control the building, so which means we want to use as little energy as possible, the first issue that we have, of course, is that every building is different, right? So you need a solution that kind of works for everything, which is not easy in practice. And then the second point is that buildings are usually not empty, right? If they were empty, you can just turn everything off and use very little energy. But of course, when people are inside, you need to make sure that they are what we call comfortable. And this is the case for every building, but it gets even harder in our case, or when new technologies come into play, right? So when we think about Solskin, which puts panels in front of windows like this, this is great because it produces electricity, right? It taps into this facade business and where it's usually hard to produce electricity, namely in front of the windows. But of course, once you start touching to the windows, you also interact with the view from the inside. You interact with the amount of daylight that people receive, and also with the thermal properties of the building. Because depending on how the panels are oriented, you also create more or less shading to your building. And again, in the summer, it might be good because you use less energy for cooling. But in winter, you might actually want the contrary, right? You might want to have as much sun as possible heating your window to warm you up. So this makes it a very, very complicated problem. And because of that, there is basically no solution that would work all the time. So in practice, in buildings, usually the way they are controlled is through rule-based controllers, which means, if the temperature is getting too low, then we turn on the heating. If it's too high, we turn on the cooling, and so on and so forth. And now for us, that doesn't really work. If you think about this Solskin system with many panels moving in every direction, designing these rules would be basically impossible. And this is where AI comes into play, right? Because AI based on data can be very flexible. So it would be able to adapt to different buildings, to different systems, to different people. And we know that if we do it correctly, you can have up to 30% of energy savings. Of course, this is depending on the building and depending on how you do it. But in general, we know that buildings are not operated optimally, and we can do much, much better. And when we bring this Solskin system, we want to make sure that we also impact the building as a whole, and that we're not just, giving this new robotic fancy system on the facade. Now, if AI is so great and can bring these many savings, why isn't it everywhere, right? It's because, of course, reality is much, much harder than doing everything in simulation. One problem is that a lot of these AI models or these advanced controllers, they need a model, right? And so you need a model of how your building is behaving, how your system is behaving. And this is in practice really hard to have. And again, if you think about Solskin, it's a soft robotic system. So it has soft arms, which are notoriously hard to model. So this is also not really feasible. And even if you were to spend like 2 weeks designing the perfect model of your building, then it would not work for the building next door, right? Because every building, again, is different and you run into that issue. So this is why a lot of people are arguing that we should try to bypass models and directly use the system that we have to learn and to teach our AI what to do. Now, the issue with that is that it takes way too long to converge in general, because your AI needs to try something. For example, for one day, you turn on the heating quite a bit, and then you look at the end of the day, was it good? Was it not good? And then you try to adapt the next day, and so on and so forth. And it takes a long time for the system to figure out how to do things in the best way. And also it can take catastrophic decisions, what we call, which means that it might just try to turn off the heating during the coldest day of the year, just to see what happens and see if it's a good idea or not. So yeah, there are still many hurdles, I would say, but these are more like on the theoretical or technological level. I think this can be bypassed. But even if you have a very good AI, you still face many, many problems in the real world when you try to go to a physical building. And the first one being, of course, that AI needs access to data, right? And in newer buildings, it's a bit easier, but in many, many buildings, you actually don't have data. And if you want your AI to maintain a good temperature in your building, then you need to have a measure of how this temperature is actually working, and so on and so forth. And then the second point is about actuation, which is a link to that, is even if you have a great AI and it's able to tell you, okay, now is when you should turn on your heating, how does it do that in practice? And a lot of buildings, it's still manual. You have your radiator, you change the thermostat, but you cannot really directly tell the thing to turn on or off. And this is a big, big limitation when you try to deploy any advanced methods in a building. And then, of course, the final one is about acceptance. I would say that there are still a lot of people who would not be very comfortable with having everything fully automatized in their building. So that's another question. And this is why I would say, like in a lot of cases, like these advanced methods are still not widely deployed, and we're still using sort of these simple rules to control our buildings. And even when we have that, one question that is sort of always or a bit put aside is what it means to be comfortable, right? So this is again something that's been a question for a long, long time. We've like tried to do many, many comfort models, but they're basically all wrong. And the main point is, of course, comfort is extremely personal, right? Everybody is different, and everybody wants something different from the system. And so this is again very complicated to implement in practice, and people just usually just don't talk about it. And when we say we want comfort inside the building, it's just, yeah, we want the temperature to be roughly something that people like. But of course, it goes much further than that. And this is where we also see a great potential for AI. And this is what we are actually developing now at Solskin for our system. We want it to be personalized or preference-based, which means we want the system to really learn from the users. So essentially, instead of trying to understand what comfort is and then telling the AI to maximize this notion of comfort, we just tell the AI to do whatever the user wants. or to actually try to do what the user wants and balancing it with energy consumption, energy production in the case of Solskin. So it becomes this multi-objective optimization problem. And the main idea is, yeah, we don't really care why the user is moving the panels at that point in time. What we care about is that, yeah, in this situation, this is what the user wants. And the AI should know that, should learn that, so that the next time it can adapt to it and it can do it instead of the user. So I think this is where AI also has a great potential. And this is where it can help us really make these buildings that we have smarter, hopefully. Now, even if we can do that, we still have these many issues that I mentioned about data and actuation. But this is also something that we faced at Zurich Soft Robotics. In general, it's easy for us to install the system and to control our system, but if you want to interface with the building behind it to make the synergy better, and you have a lot of challenges. And then, of course, one of the big issues that is still unsolved and will not be solved by this approach is how to reconcile different opinions inside a building, which is linked to this notion that comfort is really personal. So two people might want extremely different things, and this is a really hard problem to solve, which we need to tackle at some point. And I would say, in the case of buildings in particular, this is not really linked to AI directly, but we have a lot of different stakeholders. For Solskin, for example, like the building owner usually cares about producing as much electricity as possible. The person renting the building usually cares about decreasing the energy costs, which is another behavior of Solskin. And of course, the people who are actually sitting in the rooms care mostly about comfort and would like the system to do yet another thing. And so reconciling all these different opinions and objectives is always a bit of a challenge. But in general, I think AI has really a great potential to help us and to make these buildings smarter. And yeah, I hope we can deliver that soon enough. And with that, yeah, I'm done, and I would take questions if you have any.
Done and out. Thank you,
Done and
Loris.
out.
Thank you very much for your presentation. Slightly different perspective. I will open the floor for questions, please, for Loris.
Sorry, it's me again. I was just going to kick it off, but Alexis actually sent an email, sent a question, but I'll kick it off. So do you think, Laurie, just in your head and, with what you can practically say right now, do you think this is going to be sort of the future? I think these intellectual buildings, AI buildings of the future are going to be what we're going to, what our offices are going to look like maybe in, I don't know what scale, 10, 20 years time. Do you think it's going that way, or do you think there's too much to go through yet and challenges?
Yeah, that's a good question. I think it should go in that direction for sure. I think it will ultimately. There are like still these hurdles, but for newer buildings at least, I think we should think about making them AI compatible by design, kind of, because of course it's hard to go inside an old building and it costs a lot just to change the system so that you can put an AI on top of it. So the benefits are not really there. I think for new buildings now, this will become a standard pretty soon. And all these the HVAC companies and construction companies, they start to have a lot of incentives to make sure that the building is as resilient as possible and consumes little energy. And then if you can move the people who are installing the systems, then you can do the AI on top of it.
Yeah, understood. I think it'd be difficult to get this into the UK as quick as it would be in other places, though.
I don't know about that. Yeah.
Thanks for your question, Julian. Alexi asks, what are some of the AI systems that you're using?
So it can be basically anything, right? Everything I've mentioned is sort of AI agnostic. And for even for the personalized AI that we are now developing, it can be a bit of anything. One detail I can share is that, nowadays everybody's speaking about these LLMs and these ChatGPT and everything, and that's great. But that's great when you have tens of millions of data to train from. And if you want to do that in a building, again, you won't have that. So we are living in a world where we don't have a lot of data to work with. And so we have to use slightly different techniques, usually not based on neural networks or that kind of framework, but it's essentially system agnostic. It's more about the engineering part, I would say.
Just wondering what the effect of kind of extreme weather would be on the systems.
Yeah, that's a great question. So actually, the core IP of the company is the robotic arm, and this is the soft robotic arm, right? So it's never locked in place. It's based on air and bellows, and so when the wind blows, for example, the panel can just move. You can just think about leaves in a tree. It's a bit of the same thing. So this makes it actually much more robust than any other moving system on a building facade. The fact that we don't have any electrical motors, it's all pneumatic, and it moves by air, makes it actually very robust to extreme weather conditions.
And then in terms of kind of scalability, integration with clients, what are some of the main challenges, problems that Solskin's control system and it's incorporating existing building management systems?
Yes, I'd say at the moment, like, we're not dealing with, again, not massive data, not massive systems. We're just trying to move. Even if it's thousands of panels on a big facade, right? That's not a problem for today's systems that we have. But yes, interacting with the building behind the system is where we struggle a lot, because you have many different systems. Everybody has their own protocols, and some people are also not really willing to open their building management system, and these kinds of issues. So this is the main hurdle for scalability at the moment. Yeah.
Okay, interesting. Got a question from Michael McSorley, project manager at WSP. Michael says, if you have that many different small movable solar panels, then where is all the cabling, cable containment, and electrical inverters located?
Yeah, good question. So the system is modular, and it comes in units. So all the units are pre-assembled, units of like 20 square meters, or it depends a bit on the project. They're pre-assembled, and then they're just hooked up on the facade. So the installation itself is actually fairly simple and fairly quick. And the cabling is done it goes through the tubes that you can see on the picture. Maybe I can just share quickly if I find it. Yes. So you can see this grid, this metal grid that is holding the panels, and all these tubes, all the tubes and the cabling go through that grid essentially. And then around it, we don't see it because of course it's not in front of the window, but there is the frame of the unit. And in that frame, we have all the main cables going through, and we can also place the inverter there so that it's not visible from the inside. Yeah.
Okay, interesting. Thank you, Loris. We have got another question from Andrew. I'm not sure where Andrew's from. I can't work it out from his display name in Zoom, but he asks, how is the Solskin system fixed to the external? Oh, he's from Nomura Architects. Thanks, Andrew. How is the system fixed to the external envelope of the building?
Yeah. So again, it comes in units of a certain size, depending on the window size and the size of the floors and everything. And then you have a frame around the main panels. And this frame is then hooked up to the building as an external skin. And there is usually a lot of space between the panels and the building, because the panels are also in front of the grid a little bit. So yeah, it's an external frame which is then hooked into the building, and it holds this entire grid of panels into place.
Kevin Fielding, Shepherd Robson. Have these systems been tested against extreme weather conditions, hurricane strength winds. I think I did mention about extreme weather. I'm not sure if you answered about hurricane strength winds though, Loris.
Not hurricane strength. So we have been testing it up to 100 or 120 kilometers per hour without issues under like constant wind. It should hold. Well, all the tests that we've done have been, we've never broken the system, and we pass all the regulation tests that we need to do. I'm not sure about hurricane strength winds, but it has been tested in very, very high winds. It has been tested under high UV exposure, on the rain, against rust, against hail, and all kinds of weather conditions. So yes, it is approved for operations without problem.
Excellent. Thanks for your question, Kevin, and thank you, Loris. Before we wrap up completely, I'd like to briefly reflect on our 4 keynotes today and some of the key insights from today's session. Firstly, we heard from Cesar Fagachan Pinzani from Alta. Cesar showed how AI is transforming early stage design through digital twins, configurators, and automation. His platform enables real-time exploration of building options while staying connected to cost, materials, and delivery constraints, which in turn helps to bridge the gap between design and reality. He also highlighted a key challenge: adapting to different workflows across practices and driving adoption. Alta's approach combines open source AI with bespoke solutions supporting everything from student housing to customized residential projects. Our second keynote was Molly Claypool from AUAR. Molly reframed housing as a manufacturing problem, presenting AUAR's robotic microfactories that bring production directly to the site. These portable systems deliver factory quality timber construction without the need for permanent facilities powered by software that link design straight to a manufacturing. By combining robotics with physical AI, AUAR is improving speed, cost, and scalability, offering a practical new model for delivering housing at scale. We then moved on to Loris Di Natale from Zurich Soft Robotics. Loris introduced Solskin, a responsive facade system using soft robotics to optimize energy, daylight, and comfort in real time. Rather than relying on complex rules, the system uses AI to learn from user behavior and adapt over time. Built with resilient pneumatic components, it offers a flexible and modular approach to intelligent building envelopes, while highlighting the broader challenge of balancing user needs, energy goals, and system integration. And then we just heard our final presentation today from senior lecturer at Loughborough University, Shirin Dora, who focused on AI and project controls, showing how it can transform how we manage construction data. His system, construction.ai, connects information across documents to detect risks early and predict their impact on time and costs. It shifts teams from searching through information to simply asking questions and receiving clear, actionable insights. Trin's case study presented strong accuracy, pointing to a real opportunity to improve decision making and productivity across projects. So, thank you for attending today's micro conference. I think taken all together, today's speakers have shown that AI is not just a future concept, it's already reshaping how we design, build, and manage the built environment. The challenge now is how quickly and effectively to adopt these tools to unlock their full potential. Thank you again to all our speakers and to everyone who joined us today. Please do keep going back to buildingdigital.com. Thank you again from me, and enjoy the rest of your day. Thank you very much.